This is lecture 9 in this course on electric machine design, and in this lecture we are going to talk about the design of the core. If you remember, in the previous lectures we talked about the output equations for the single phase and three phase core and shell type transformers. We now shift focus to the design of the core. So as you know, that core is the part of the magnetic circuit, and it is responsible for the flow of the flux. So it is made of silicon steel laminations, and these laminations are about 0.3 to 0.5 mm in thickness, and they are separated by varnish layers. So you apply a layer of varnish in between two successive layers. So for small transformers we use rectangular cores, and the nature of the windings is either circular or rectangular. Coil, right? However, for large size transformers, I have talked about this in the previous lectures as well. In the large transformers, this design of rectangular core is not suitable due to the various factors which I'll talk about in a bit. So in general, it is to be noted that you have circular cores with circular coils. Now, why is this? This is because the circular core occupies less space when it is wound up by circular coils, and also the mechanical forces in the transformers, in these large transformers, in short circuit conditions, it is seen that the circular shape is ideal, and it provides does not allow the winding to get damaged. So that's why this circular core with these circular coils is used. Okay, so this circular core, as you must have as I discussed in the previous lectures, this circular core is made up of different types of laminations. These circular cores made up of different laminations. Okay, so what are these laminations? These laminations are this is the EI laminations. Then there are the These are the EE laminations. They are usually used for shell type. Let me move this to the left so that we have enough space. And then of course you have the L type lamination. L laminations, and you have this is the UI type laminations. Okay, so these are the core type laminations. Okay, so as I mentioned earlier, laminated cores have to be used. Laminated cores have to be used. So we have laminations are to be used. So we have laminations of different sizes, right? So what we do, in order to obtain a circular section, we assume that an infinite number of we make a that sorry, to obtain a circular section, we approximate the circular section as a stepped core with infinite number of steps. We assume infinite number of steps. So what does this mean? I'll show you this in a bit. So if you have, let's say, one lamination like this, the other one will be slightly lesser, and then the next one will be more lesser, then going on like this, right? So this is a stepped core with infinite section. So if this is one end, so if you see, this sort of makes up a circle. So this is how you generate a circular cross section. But this having this infinite number of steps is not practical for practical purposes, as in seeing the physical size of these steps. So there is a maximum number of steps that can be put, right? So what happens when you put the maximum number of steps in this stepped core, you can easily make you can easily approximate the circular cross section. And what happens because of this is that you can use circular coils over it. Okay, so this circular cross section or the stepped core is also known as the cruciform core. We have talked about this in the previous lecture, cruciform core. So in general, you can have the core. It can be of three major types. It can be a stepped core, it can be a square core, it can be a rectangular core. step could be cruciform, two step, it could be a three step, or a four step core, right? So this is in general the classification of the cores. So if you have stepped core of two steps, so it's called a cruciform core. Then you call the next step a next core of three steps and four steps, and like so. So let me draw this. Let me draw this for you. If we have a rectangle like this, if these are the laminations, right? So there's a circle that goes around this, right? Then you have an outer circle as well. Make this a little neater. Okay, so this is the square core. The next core, and let's see that. Sorry, the next core is like this, and it has the next step like this, the next step like this, and the above step like this. So this is a four-stepped cruciform core. And if you increase this step, if you have four of them or five of them, that qualifies as a multi-stepped core. I will not draw the figure here. Multi-stepped core. So instead of the four of these, you will have multiple steps like this. One, the next one, then the next, and like so, right? So this is called as a multi-stepped core. Okay, so moving ahead, we talk about this circle, this imaginary circle around this core. This circle, it is not actually present there, but you can think of this circle being, as an imaginary circle. So this circle is known as the circumscribing circle, right? So what happens? What happens is that this circumscribing circle is used to determine the areas. So we are going to talk about these areas now. So what happens? There is a factor known as the stacking factor, and that factor is known as Ks, the stacking factor, and it is equal to net core area AI divided by the gross core, this is called net core section over gross cross section, gross core section rather. So why is this different? Because like I said earlier, you have these laminations, and on this lamination you apply a thin coat of varnish, right? Then you have the next layer, then you have another coat of varnish. So what happens, this coat of varnish is also, I mean, the total area, the assembly also has a portion of the insulation in it, right? So this green portion, this green varnish is actually the insulation. It's not the core. The core is in blue, and you have this layer of varnish. So that's why there are two different areas. You have the net core section, which comprises of the core only, and this gross core section is the core with the varnish. So this stacking factor ks is usually has a value of 0.85 to 0.9. All right. So once you have this once you have discussed, I mean, read about this stacking factor ks, we will then talk about what this area, this ai ag, and we will talk about some more ratios. So first we shift to a square core. So if you have a square core, by a square core I mean it has a square cross section, and I think of a imaginary circle. Right, let me draw this for you. Let me draw the circle first. For a square core, what happens, this d is the diagonal, and area a is the length of any side. So what is the gross core area for the square core? AGI. It is a times a, isn't it? Where a is the side of the square. Now d is the diagonal. You know from Pythagoras theorem that this diagonal d is root 2 times a. So if you put in, instead of a, if you have the diagonal given, the gross core area AGI can be written as d square by 2, or you can write this as 0.5 d square. Okay, this is the gross core area. Okay, I'll write it here, gross core area AGI. Then you have the net core area. Net core area AI is equal to the stacking factor times the gross core area AGI. So AI is equal to KS times AGI, and if you take this KS to be equal to 0.9 and substitute this AGI, you come to the conclusion that this net core area is 0.45 times d square. Okay, this is one expression. The net core area is 0.45 times d squared. Fine. Next, we want to find out the utilization of the available space. utilization of the available space in the transformer. So for that, we see that the area of the circumscribing circle ACC, area of the circumscribing circle ACC is equal to, what is it? If you look at this, pi d square by 4, isn't it? It will be pi d square by 4. It will be pi r square. Area of circle is pi r square. Since r is equal to d by 2, you get this ACC equal to pi by 4 d square. So the ratio of the net core area to the area of the circumscribing circle that is given by AI over ACC, which is equal to 0.45 d square over pi by 4 d square. So that is comes out to be around 0.58. So this is one important factor. The ratio of the net core area to the area of the circumscribing circle is 0.58, and the ratio of the gross core area to the area of the circumscribing circle is 0.5 d square over pi by 4 d square. So that is equal to 0.64. So these are two ratios that we need to keep in mind. Okay. All right. Next, we talk about, so this is all about the square core. So this is area of the net core area is 0.45 d square, and the gross core area is 0.5 d square. Then you have the circumscribing circle pi by 4 d square. Then the ratio of the net core area to the gross area of the circumscribing circle is this. And then you have the ratio of the gross core area to the area of the circumscribing circle, that is 0.64. Fine. Okay. Next, we talk about a stepped core. So a stepped core looks something like this. You have the inner part, which the inner rectangle, which looks something like this, and then you have right. So this is part 1, and this is this, and this is part 2. In this part we have the diagonal D. This has the width B, and this length is A. So this is a stepped core. Okay. So how do you calculate gross core area and net core area? You calculate the area of this rectangle, and then you you calculate the area of this rectangle, then add this, then you have the area of the circumscribing circle, then you can get this AGI and AI. So in general, you must remember that this gross core area for this case comes out to be 0.618 d square. It is easy to calculate this. I will leave this as an assignment to you guys. You please find out these expressions. The gross core area is 0.618 d square. The net core area is 0.56 d squared. And if you assume this is because when you assume ks equal to be 0.9, and the ratio which we calculated earlier, AI over ACC is equal to 0.71 and AGI over ACC is 0.79. So these four ratios you can easily find out, and you must keep these ratios in mind. Okay, so I leave the derivation of these expressions as an assignment to you. Derive these ratios. Okay, so you will be able to easily derive this. Okay, so this is about the design of the core, and just for your information I will give you some extra bit of information here. If you have the ratio here, it is AGI over ACC, AI over ACC. This is a square core. I will summarize these results. Two-step these ratios are 0.64 and 0.58, 0.79 over 0.71, this is 0.84, this is 0.75, this is 0.87, and this is 0.78. Okay, so this is all about the design of the core. We now talk about the design of the yoke. So yoke, what is the yoke? The yoke is the portion that connects the legs and provides the least reluctance path. Okay, so we have talked about this before. The yoke, it does not have the iron winding, does not have windings. So what do? We can minimize the iron losses by increasing the area. By increasing area, right? What happens because of this increase in area? You reduce flux density B, right? We have talked about this in the previous lectures. So you have to keep in mind that the yoke is the yoke area is about 20% higher than the leg area. It is about 20% higher than the leg area. So these yoke sections, they could be rectangular, they could be cruciform, right? So what do you mean by a rectangular yoke? A rectangular yoke looks something like this. This is a rectangular yoke, rectangular leg and yoke. So this dimension, this is A, this is the dimension dy, we call it depth of yoke, and this dimension is hy or height of the yoke. Okay, so A is the largest stamping, width of the largest stamping. Dy, A is the, I'll repeat, A is the width of the largest stamping, dy is the depth of the yoke, and hy is the height of the yoke. Similarly, you can have a rectangular yoke and a cruciform leg. So what do I mean by that? I will show you that here. I have a rectangular yoke I hope you are able to make what I'm trying to you are able to make out what I'm trying to show you. So this is one face like this, and this face is like this. Okay, and this is faces like this. Okay, so what is this? This is the dimension A is from this end to this end, and this is, so this is a rectangular leg and yoke. This is the rectangular yoke and cruciform leg. Of course, you can have cruciform yoke and cruciform leg as well. I will not draw this here, so you understand the point. This is a rectangular leg and yoke. This is a rectangular leg and a cruciform leg. Rectangular yoke and cruciform leg. All right. So for a rectangular yoke, as in for this case, the rectangular yoke, the depth dy of the yoke is going to be the same as the depth of the yoke, right? So, and this is equal to the largest core stamping A. Okay, so the depth of the, I'll write this down for you. The for rectangular yoke, what happens, the depth dy is the same as the depth of the core, and this is equal to the largest core stamping A. The height of the yoke hy, it is equal to 1 to 1.5 times the width of the leg. The width of the leg here is A. So the height of the yoke is taken to be 1 to 1.5 times the width of the leg. So area of the yoke AY, it is equal to dy times hy, which is equal to 1.15 to 1.2 times AGI, and this is valid for hot rolled steels. And AY, since this is cold rolled steel, so area of the yoke is always equal to the gross iron area or the gross core area for cold rolled steels. Because you don't need to worry about you can have higher flux densities in cold rolled steel, so there you don't increase the area for cold rolled steels. Okay, the last topic that we will discuss today is the window and core proportions. The window or core proportions. The area of the window AW is equal to Q in kVA, that is the output that we derived yesterday in the last class, divided by 2.22 or 3.33 or wait a second, let me just, this is area of the window, let me, or 6.66 times F delta BM AI kW into 10 to the power 3, right? So once you have all of these, you can calculate the area of the window. So if you know the power, if you know which type of transformer it is, whether it's a single phase transformer or it's a three-phase transformer, and whether it's shell or core, you can choose from these three parameters. Then you have the frequency, the current density delta, BM flux density, AI iron area, and kW window space factor times 10 to the power 3. You can calculate the area of the window. Fine. So if you have the area of the window that is known, you can also compute the width WW and the height of the window from it. So this is another factor that you have to keep in mind. And also you have to keep in mind that in order to limit the leakage reactance, what is done, this height HW is usually made more than the width of the transformer. So this HW over WW ratio is usually between 2.5 to 3.5. So the height is about 2.5 times the width. So with this we conclude today's lecture, and summarizing, I'll just briefly go over what we discussed today. We started off with a description of the core. We saw how what different types of laminations are used. We talked about the types of the cores. Then we talked about cruciform and square shaped cores. We talked about this stacking factor Ks. Then we calculated some important ratios, the net iron area, the gross iron area, and the ratio between them. We did this for the stepped core as well. And then we talked about the design of the yoke. And lastly, we discussed about the window and core proportions. So we said that the height of the window is always greater than the width of the window, and this factor is between 2.5 to 3.5. So in the next lecture, we will talk about the overall dimensions of the transformers, and after that we will do some numericals, and that will help us in better understanding all that we have studied so far. So thank you, and I'll see you in the next lecture.